Hello guys, today I will explain you about PCA, which is known as Principal Component Analysis. This is used for data compression when we have a very high dimensional data. When I say high dimensional data, then I mean to say the data in which the number of variables or the number of columns are very high. Say maybe 10 or 100 or maybe 1000 or 10,000s. So if we have very high dimensional data where the number of variables grows very high, in that case we might require data compression techniques. One of the data reduction technique is principal component analysis. So in this I will explain what are the things which we should first see in the data before we actually perform the principal component analysis. So let's take some data and then we try to figure out that how we can reduce that data into lesser number of variables. So say we have 100 variables or 100 columns in the data, and we just require that data to be converted into 2 or 3 variables. In that case, what we do is we perform a principal component analysis on the data, and all those 100 variables are then compressed down into 2 or 3 variables, which explains the complete variance in the data, almost 90 or 95% of the variance which is present in the data. So once we get the 2 or 3 variables after the reduction of the data, we can visualize that data. If there is any groupings in the data or whatever we want to do, we can also use that data for predictive analytics. That I will tell you later on, but first let's begin with taking some data and then have a look what it is. Let's take this data iris, which is a very familiar data which is already present in this R. So let's store this iris data in the object df. So now we can see that this data is present here, and here we have 150 observations. And here, just for the sake of explanation, I'm not taking a very high dimensional data, but I will be giving an exercise, or I will also show you the data where is a very high number of variables are there. Usually like 100 or thousands or millions of columns are also present in the data, like images, sounds, and in that data it is very much required to compress that data into lower dimensions. But just for the sake of understanding, let's take only a simple data where we have just few rows, like 150 rows and 5 columns. But out of these 5 columns, we see here that there is sepal length, sepal width, petal length, petal width. These are 4 numerical variables, and this is a species which is telling the categorization of the data into 3. So there are 3 species: Setosa, versicolor, and virginica. So based on these 4 parameters, like features, sepal length, sepal width, and petal width, the data is represented into 3 categories. Now what we want to do using the principal component analysis, instead of taking the 4 variables, these 4 variables, we would just require only 2 variables to explain this data, and see if that those 2 variables can explain this data properly on the basis of a species or not. We won't be using this as species variable while doing the performing this principal component analysis, but just take these 4 columns and then perform the principal component analysis and see if we can get any 2 variables which can explain the variance in the data, maximum variance in the data. So let's see how the data is looking like. So we already saw that data. So data is here in the console. We can see that data is present here. Now let's see the structure of this data frame. The structure, let's see, the first 4 columns are numeric, and this 5th column is a species which is telling about the class of the observations or class of the rows. There are only 3 classes in this data, which is Setosa versicolor in Virginica, we won't be using this fifth column. So before we dive into this principal component analysis of this data, let's first see that how this data is distributed for each of the variables, so that we get to know that what we need to perform, what we need to do before actually we do the principal component analysis. So let's run this code, this line of code. So this par mfro, this I've just written for 2 rows and 2 columns. So we have 2 by 2 uh, matrix of this plots, and we are plotting the histogram for each of these 4 columns. So we can see that here the distribution. So the histogram of sepal length is here and sepal width is here, petal length, petal width. From the distribution we see that the distribution is not normal. So if you're not familiar of what does normal mean, normal is usually something which is having a 0 mean and deviation as variance as 1. And if you don't know about the variance, so variance is nothing about but it is just the how much varying the data is around the mean value. So here we can see that this sepal length is starting from here around 0 and goes till 8, and we have some mean value in between, but we have lot of observations which are uh, lot less than this mean value, and lot of variables, lot of observations which are higher than this mean. So this deviation, standard deviation or the variance, explains that how much of the observations are far away from the mean of mean of all the observations. So we can see that this is not normal. The normal distribution is almost bell shaped. You can see that it's like that, but here we see that there is a little right skewness. It is not completely symmetric. Had it been completely symmetric, we can say that this is a completely normal distribution, but this is not normal distributed. This on the right hand side sepal width, this seems like a little bit of normal distribution, but still there is a little right skewed where we see that a little bit higher long tail on the right side. Again, it is not a completely symmetric where we can say that it is completely symmetric around the mid value, or we can say mean value. On this petal length we see that there is a distribution around here, but then there is again a cloud of observations which is far away. There is a separation between these two distributions. So this is not at all a normal distribution, and this again is also not a normal distribution. So it's not a explicit condition for performing principal component analysis, but it is worth seeing that how the distribution of the variables looks like. Because if some of the data is varying a lot, then one of the variable might affect a lot into the PCA. So it may over dominate. So one of the variable may over dominate in the principal component analysis, which may not give interpretable results, or which may not give good results. So before performing principal component analysis, we should know what is the variance in each of the variable. Is it skewed or not? Is it a normally distributed or not? If it is not, then we need to scale the data, which is called scaling the data. When we say that scale, there are a lot of scaling methods which we can use for scaling the data. Some of the techniques for scaling is like min-max normalization or standard deviation normalization, where what we do is in a standard deviation normalization, we subtract each of the observation from the mean value of the observations, and then divide by the standard deviation. So what it is actually doing is it is standardizing the data. So you need not go into the statistics part of this, but you just get to know, you just have to know that there is, which is called as normalization, standard deviation normalization technique, or our min max normalization. Other normalization techniques are also there. Also, there are methods which are used for removing this skewness, which is like here we have right skewed, here we have little left skewed, here also we have little left skewed. So this skewness creates little problem when we perform the principal component analysis. So it is better to do some kind of transformation in the data before you actually actually do principal component analysis. So two things are very important. First thing is to scaling the data, so that you have something we can say that the data is in the range of 0 to 1, or all the data is in the range of -1 to 1, so that none of the variable is over dominating in that analysis. So once the data is in the range, say 0 to 1, all the variables are in the range like 0 to 1 or -1 to 1, so just for an example, and there is no like skewness problem in the data. um, so these two things you have to figure it out. If there is this issue, you just have to do the scaling using one of the technique, and the transformation of the data, which is called Box-Cox transformation, which is being used for skewness. And once it is done, you can then perform the principal component analysis. So let's see, after distribution, let's see what's next. So what is the correlation among the variables? Correlation is something which tells about that if the two variables are changing linearly together, increasing, linearly increasing, or linearly decreasing. If there is no relation at all between the two variables, then the correlation is 0. If there is perfect correlation, then it makes +1 when they are linearly increasing, and -1 if they are linearly decreasing. But it is mostly it is not +1 or 0 mostly. But if there are good correlation, you would get something around 0.7, 0.8 or something. But it totally depends on the data in hand. So let's see in the data, in the current data which we have, see if there is any kind of correlation. So let's import this library core plot and see the correlation. So here we see that correlation, this darker colors are like 1 correlation, and this light colors, this dark color is -1. So these are lesser correlated values, these, this. So sepal length is highly correlated with itself. That is, of course, that is 1, because these are just representation. Sepal width is correlated with itself, but again that is not an informative thing to take into account. But sepal length, if you see that it is highly correlated with petal length also, it is highly correlated with petal width. Again, petal length is correlated with this, petal length is also correlated with this. So we can see that there is correlation. If you just want to see the correlation matrix, you can see that here the values, actual values. Sepal width with sepal length is -0.117. Petal length is correlated with sepal length with 0.87. Petal width with sepal length is highly correlated with value of 0.817. So there is a correlation between the variables. So one of the I told you about the scaling and the skewness things, the scaling thing which you need to do, and the thing. Third thing which you need to see, if there is any correlation or not. If there is no correlation, it doesn't make much sense to do the principal component analysis. It is usually done when there is a correlation between among the variables. When you have a very high dimensional data, there is of course a lot there. Mostly it happens that the most many of the variables are very highly correlated, and then when you perform the principal component analysis, it is squeeze out some of the features, new features like 2 or 3, 4 variables, which can explain like 99% of the variance in the data. So let's see that how much skewness was in the data. So I will import this moments library to use the function skewness. Here you see that sepal length is was little right skewed, as I showed in the earlier histogram, and petal length and petal width was little left skewed, which was shown in the histogram. You can see again is left skewed and there's a little right skewed. Now if you want to see the variance in the data, you just use the function var and then apply. So it is showing the variance in all of the four variables. We can see that there is a variance in petal length which is comparatively higher than others. So it is saying that there is some of the variables like petal length is having high variability. So when we scale the data, then all variables are on the same scale, and when we are performing the some transformation like Box-Cox transformation, then the skewness problem is gone. Like this skewness values minus zero point 0.1, these skewness becomes tries to be almost zero, so that it is normally distributed. So first thing which I told is the scaling. Second thing is the Box-Cox transformation if there is some skewness problem. Third thing is this correlation value which you need to see if there is not. Then let's take the data frame and then remove the fifth column, which is the species. We are not taking into that account because it is not a numeric variable in this data. And then like import the character library. And let's perform the Box-Cox transformation using this function pre-process. Put the data frame name here, PCADF, which is this one, and the method is Box-Cox. So this like this, and then get this PCADF data from the predict function. So what this function, these two functions together do is first it process the data pre Box-Cox, and then it recreates the data after the transformation. So this is the transformed data PCADF. Now this was actually the function which is actually performing the transformation. Then this transformation is being performed on the data PCADF, which was this one. So now the PCADF is not the earlier older one, but it is the transformed data. Now this will remove a little bit of skewness. See, we can see that the skewness of first two variables is gone. It is almost zero. Third and fourth is not gone, but because it was not possible, the model was this Box-Cox transformation tried to remove the skewness, but it could not remove. But the first two variables has removed. This is the best which you could do. So Box-Cox transformation we have done. Now we need to perform the scaling or scaling thing. So what we can do is here we can use the scale function also. So it will do the scale and also the eliminate the skewness by using the Box-Cox transformation. Let's take the PCDF again and then do this again and see the skewness is gone, and the scaling is also, you can see that the distributions again, the distribution looks like this. So this is how we tried to do the Box-Cox transformation. Now I will explain you about the so now what I am going to do is to perform the principal component analysis. So we have done the scaling so that all the variables are scaled to the say they are on the same scale, say 0 to 1 or minus 1 to 1. It's a matter of scaling what kind of scale we have done. So no other transformation we are no I will show you other kind of transformation which is called log transformation and all those things, but just remember that Box-Cox is being used for removing the skewness. Scaling is done to just keep all the variables on the same scale. These two things are very important. Once you have done this thing, Just use the function prcomp, put the data frame name, which is the transformed data frame, which is the Box-Cox transformed data and the scale data. We are not using the centering right now. Centering means like you are subtracting the mean from all the observations in each of the variables. So we are not doing the centering because we have already scaled the data, and we are not doing this thing. Just fit this model, see how this data looks like. So these are the new variables created, which are known as PC1, PC2, PC3, PC4. If you check the summary of this model, here it shows the standard deviation of the PC1, PC2, PC3, PC4. There are 4 PC principal components because we had 4 variables on which we performed the principal component analysis. The aim was to get the uncorrelated, or you can say orthogonal variables. So PC1 is orthogonal to PC2, and all these 4 variables are orthogonal. Sorry. So the orthogonal means their correlation is 0. Earlier we had the 4 variables, which was sepal length, sepal width, petal length, petal width. They were correlated. Now we created new features, which are now the linear combination of the original variables, but they don't have any correlation among them. So PC1 is now a linear combination of sepal length, sepal width, petal width. Again, PC2 is also some linear function of all these 4, but they are such linear functions so that this PC1 is not correlated to PC2 or PC3 or PC4, and for it is same for all the PCs. PC1 will be the variable which explains most of the variance in the data. Here you can see the proportion of variance. So 98.6% of the data variance is being explained by PC1. Only 1% is being explained by PC2, and the rest of the variance is being explained by PC3 and PC4. So we can say that instead of taking the 4 variables in the data like sepal length, petal width, all these 4 variables, we can just take the PC1 and we can explain the data. So what we will do is we will visualize this data in the 2 dimensions, and also we can visualize this thing in the 3 dimensions. So we will do it later. First, let's plot the plot, which is called Scree Plot. This is nothing, just which shows the cumulative proportion of the variances, which is like you can see that the PC1, PC2, PC3, PC4, PC1 explains around 98 point something variance in the data, just shown here, 98.6 variance. This is called a Scree Plot. If you want to see again, you can do it like this. Which is also again showing the same thing, proportion of variance. So if you want to see that what is the structure of model, what it contains like list of standard deviation, rotation, center, scale, and X. I will explain you that standard deviation explains what is the deviation, what is the variance explained by each of the PCs. Okay, so and X is the transformed data now. It is having 150 observations and 4 variables, 4 new features, which is PC1, PC2, PC3, PC4. This X variable you can use it for your further analysis. It could be any analysis you wanted to do, any kind of simple business analysis, or you could use it for predictive analysis, or you could use for supervised clustering, or anything you could use for this data X. It is the same as the original data, 150 observations, 4 variables, but these 4 variables are the new orthogonal variables, uncorrelated variables, which are created from the original variables after the PC. Now let's import this GGBI plot you can just install it using this commands, these two. What it is showing, you just run this command. What it is showing is the PC1 explained 98.6% and the PC2 1.2%. Here you can see these original four variables. PC1 is along this, so you can say the sepal length is just 180-degree opposite to the PC1, you can say, and petal length and petal width is just negative of PC2. So we can say that PC1 is negative of sepal length because it is negative side of the PC1. So we can say almost. So PC1 is minus of sepal length plus minus of little bit of sepal width plus minus of little bit of petal length plus 0 times of this, because so this is PC1 is now a linear combination of all these four variables. It is you're not concerned more of this thing, but just you can see that there is, you can see the groupings of setosa, versicolor and virginica, all these are clustered at different locations. So PC1 and PC2 in itself can show the data points and they are clustered differently, you can see here. In the next video I will explain you how you can use this for clustering, principal component analysis, and then you can do the clustering in the data, and if you can check if there are certain clusters in the data or not. Thanks for watching this video. Thank you.